All right, people, prepare to have the hidden truths about inclines revealed to you in all of their glory. Um, you've been doing lots of problems with inclined planes, applying Newton's laws to motion or objects on inclines. And here's some more practice. And this isn't one of your homework problems. It's not one of the problems we did in class. But follow this problem, and it should give you some more practice dealing with inclines. All right. So before you start any problem, make sure you draw a picture, define positive and negative x and y direction. So, with these inclines, what we've been doing is, or what I like to do is I like to call the direction that's parallel to the surface of the incline the x direction, and the direction that's perpendicular to the surface of the incline the y direction. So not vertical and horizontal in this case. And we need to draw a free body diagram. So the forces acting on the crate would be the normal force, the force of gravity, the weight of the crate itself, and friction pointing up the incline. And the force of gravity, all right, now the force of gravity points straight down. That's not the y direction in our picture here. So the force of gravity would have a y component and an x component. Okay, so keep that in mind as we go through this problem. All right, now the way we do these problems, two-dimensional vectors, well, at least in this case, the weight of the crate is a two-dimensional vector. The other ones are along one of the cardinal axes. We need to break the problem into x and y components. Right? So we might as well start doing that. And we're given the mass of the crate and the coefficient of static friction, so we'll keep that in mind as we go through here. And what we're after here is theta, the maximum angle theta before static friction fails and the crate starts to fall. And, well, we might as well write down that force law right now. Remember, in general, the force of static friction is less than or equal to mu s times the normal force. So if we want to know the maximum angle before static friction fails, what we really want is we want to know the angle where the force of friction is a maximum. Okay, it's not less than or equal to, but equal to mu s times the normal force. So we will have the net force in the x direction here is going to be, well, there's an x component of gravity in the positive x direction. That component of gravity is the opposite angle of theta in our picture. So that's going to be given by mg sine theta. And the other force in the x direction is the force of friction, and it's negative. It's pointing up the incline. And the force of friction is mu s. Well, the maximum amount of friction, static friction, is mu s Fn, and that's what we're interested in. We want to know the maximum theta before friction fails. So we want to know the theta that gives us the maximum amount of friction, or I should say, well, mu s times the normal force equals, all right, and so we're interested in the situation where the crate is not moving. So Newton's law, when the net force is equal to 0. There's no acceleration. All right, well, let's turn our attention to the y direction. And in the y direction, we will have the normal force, which points up, and the y component of gravity, which points down. So it's negative, and the y component of gravity, that component is the adjacent side to the angle. So we'll use the cosine function to give us the magnitude. And again, there's no motion in the y direction, so the net force in that direction is 0 as well. Well, here we have, so we're looking for theta. We're given mu s, we're given the mass, we're given g. We're not given the normal force, but here we have two equations, and there's two things that we don't know: the normal force and mu theta. So let's solve this equation from the normal force, this one. And then plug this in up there. So we end up getting mg sine theta minus mu s mg cosine theta equals 0. And now let's solve this expression for theta. Well, let's move one of these terms to the right hand side of the equation. So we'll get mg sine theta equals us mg cosine theta. And now here is the truth about inclines. And this, when we get to this point right here, something really neat happens. Look at both sides of these equations. Both sides have an m on them, and both sides have a g on them. Okay, so we can divide both sides by m and divide both sides by g, and those two things go away, and we end up getting sine theta equals mu s cosine theta. And remember, we're after theta here, so let's divide both sides by cosine. We get sine theta divided by cosine theta equals mu s. And what's sine over cosine? Tangent. So tangent theta equals mu s, which means theta equals the inverse tan of mu s. All right, so in this particular problem, let's see, we got, get my handy dandy calculator out here, and I want to do the inverse tan of 0.4, and I get an answer of 21.8 degrees, okay, for this particular problem. But that's not the amazing thing. The amazing thing about this problem is that, you know, and also emphasize why it's important, why it's more revealing to do problems using symbolic algebra. You notice I haven't plugged any numbers in anywhere up here. I haven't plugged any numbers in until I get to the very end, and then this allows properties, certain truths to emerge out of the math. And right here it is, that at this step m and g cancel, and the final result doesn't depend on the mass of the crate at all. It doesn't matter if it's 1 kilogram, it doesn't matter if it's 1 billion kilograms. The answer only depends on the coefficient of static friction. Also, it doesn't depend on g. It doesn't depend on the acceleration due to gravity. So this answer, theta, would be the same on Earth as it is on the Moon, as it is on Mars, as it is anywhere on any planet with any force of gravity. The answer doesn't depend on that. It only depends on the properties of the materials, mu sub s, the coefficient of static friction. Okay, so I probably blew your minds, and it's going to take you a while to collect your brains and put them back in your skulls. So I'll leave you to that.